Measuring out the ingredients. If you were a chemist, you would call this stoichiometry. In this presentation, I will consider a simple example to illustrate the key ideas of measuring out the ingredients that apply both on the beach and in the lab. We'll consider making of s'mores. Whenever you set out to make something, you need a recipe. Let's start there. In real life, to make s'mores, you begin by lighting a fire. But we will simplify and say that to make a s'more, you combine the following ingredients: 2 marshmallows, half a chocolate bar, and 1 graham cracker. At this stage, let's simplify and write a s'more as SM, 2 marshmallows as 2 MA, half a chocolate bar as 1/2 CB, and 1 graham cracker as GC. Notice that these abbreviations are just the kind of simplifications that chemists like to make for the elements. Alright, we have the recipe. The next step is to look in the cupboard and see what ingredients we have at hand. Let's say we have 6 marshmallows, 2 chocolate bars, and 4 graham crackers. We now pose the question, how many s'mores can we make? Most of you can do this in your head without ever having studied stoichiometry. Our reasoning would go along the following line of thought. I have 6 marshmallows. Each s'more contains 2 of them, so I have enough marshmallows to make 3 s'mores. Now for more complicated quantities, this would not be so simple. So let's write down as an equation what we're trying to do with these calculations. We write down 6 marshmallows, our initial amount, and then we multiply this by the ratio found in the recipe as follows: 1 s'more over 2 marshmallows. Multiplying the 2 terms, we get 3 s'mores, exactly as we expected. Writing this step out explicit will be important when we have more complicated numbers to compute. We can now carry out identical operations for the chocolate bars and graham crackers. Let me write this out. Okay. From the results, we see that we have enough chocolate bars and graham crackers to make 4 s'mores. But we only have enough marshmallows to make 3. We can conclude that we only have enough ingredients to make 3 s'mores. This answers the first question that we posed. How many s'mores can we make? Let me introduce some chemical ideas. Since we will use up all the marshmallows, but not the chocolate bars and graham crackers, we refer to the marshmallows as the limiting ingredient, or limiting reagent, since the number of marshmallows places a limit on the number of s'mores that we can make. I will now pose a second question. How many of each of the ingredients do we have at the end of our s'more making adventure? As before, you can probably figure this out in your head. For example, you need 3 graham crackers to make 3 s'mores. Since we started with 4, you will be left with 1 graham cracker at the end. This is a particularly easy example, and typically the math will be more complicated. So I am going to write down the equations associated with this reasoning in a systematic way so that we can extend the concept to more complex problems. We begin by writing down the recipe in a compact form that looks like a chemical equation. 4 marshmallows plus 1 chocolate bar plus 2 graham crackers goes to 2 s'mores. Notice that I have doubled all the ingredients in the recipe so that the recipe does not include fractions. What is important is the relative amounts of the ingredients in the equation. Note the arrow represents all the interesting steps. The bit where you collect the wood, build the fire, roast the marshmallows to just the right point of doneness, and put everything together quickly so that the chocolate partially melts. At the moment, we are only concerned with measuring out the amounts and predicting how much we will get. Now, below each of the ingredients, we will write down the starting amount. I do this in a row with an I at the front. Here I stands for the initial amounts. In the next row, I write down the change in the ingredients. Here C denotes change. We've already worked out the problem for marshmallows. All 6 are used up. Since they are lost, we write minus 6. To figure out the number of chocolate bars left, I will carry out an aside calculation. Here we see that if I have 6 marshmallows in making the s'mores, and 1 chocolate bar is used for every 4 marshmallows. 1 chocolate bar per 4 marshmallows, which I'll write as a fraction. Multiplying these two quantities, we find that 3/2 of a chocolate bar are used. Likewise, I use up 1 graham cracker for every 2 marshmallows, so that I will use up 3 graham crackers. You should be able to write down this equation. In the third row, I write down the end amounts. This is just the sum of the initial plus the change. I denote this row with an E for end. For example, I started with 2 chocolate bars. I used up 3/2 of chocolate bars, so I am left with half a chocolate bar. This algorithm for finding the final ingredients is often referred to as an ICE table, where each letter corresponds to a row in the table. An important last check is a reality check. We expect to get 3 marshmallows, but it turns out that our friend, whom we entrusted with the making of the s'mores, claims that we only have 2. Our expectations have not been met. We can quantify this disparity between expectation and reality using a quantity known as percent yield. It could be written as follows. It is just the ratio of actual and expected yields times 100%. In this case, we get a 67% yield. Let me now review the 3 central ingredients of our calculations. We have learned about limiting reagents and determined a way to determine the identity of the limiting reagent. We have learned about ICE tables for calculating the final amounts. Finally, we have recognized that our expectations are not always met, and we can express this in the making of s'mores as a percent yield.